All right, let's dive right in. Inside your head, right now, is the most powerful command center in the known universe. And it doesn't run on electricity, not really. It runs on a symphony of chemicals. Today, we're going to learn the notes to that symphony. We're going to learn the language of the brain.
So just think about that for a second. Every single thing you think, feel, or do, it's all being directed by a complex chemical code. And that brings us to the big question we're tackling today. What if we could actually crack that code? So, before you can crack any code, you have to learn the language, right? You got to understand the grammar. For the brain, that language is all about how its billions of nerve cells, its neurons, talk to each other. So let's get into the rules of the road.
Okay, so the official scientific name for this whole process is neurohumoral transmission. I know, it sounds super complicated, but it's really just a fancy way of saying that our nervous system uses chemical messengers to send signals back and forth. That's it.
But it's not just one simple kind of conversation. There are at least four different ways these messages get sent. You've got neurotransmission, which is like sending a quick, direct text message. Then there's neuromodulation, which is more like adjusting the volume on the whole conversation, making it louder or quieter. Neuromediation uses a sort of middleman to relay the message. And then you have neurotrophic effects, which are all about long-term stuff, like growth and changing the physical structure of the neurons. It's a way more complex language than you might think. So, with all that going on, where do you even start? Well, you start with the two most important words in the brain's entire vocabulary: go and stop. Let's meet the brain's main gas pedal, and its brakes.
The brain's primary brake pedal is a chemical called GABA. Its whole job is to be inhibitory, which just means it tells neurons, hey, calm down, slow your roll, stop firing. It's basically the shh signal for the entire nervous system. And to really understand where GABA even comes from, we're diving straight into our source material here. As you can see, it often starts out as these really complex handwritten notes. Our job in this explainer is to translate this stuff into something that actually makes sense.
So, once we map out those notes, what we find is this beautifully simple three-step process for making the brain's brake pedal. It all starts with a molecule called glutamine. One enzyme turns that into glutamate, then another enzyme turns that into GABA. It's like a perfect little chemical assembly line.
And hey, what about that middle step, glutamate? Well, it turns out that's not just some random stop along the way. Glutamate is the other side of the coin. It's the brain's main gas pedal. It's the most important excitatory signal, telling neurons to fire, to get going, to get active. This stuff is absolutely critical for things like learning and making new memories.
So here you can really see this fundamental push and pull that's happening in your brain all the time. GABA is hitting the brakes, reducing activity. Glutamate is hitting the gas, increasing activity. And this constant, delicate balancing act is what allows your brain to do everything from falling into a deep sleep to focusing intensely on a problem.
Okay, so we've got the basics down. Stop and go. But our experience of life is a lot more nuanced than that, right? So now let's look at the brain's fine tuners. The chemicals that add all the color and texture to our moods, our motivations, and even how we move. First up is one you've probably heard of, serotonin. Now, serotonin isn't just about simple on-off signals. It's more like a master regulator, setting the whole background tone for your brain. It plays a huge role in your mood, sure, but also your social behavior, your sleep cycles, even your body's thermostat. It's doing a lot.
And then there's dopamine. This is the chemical of motivation, of reward. It's the thing that pushes you to go after things you enjoy, and it helps coordinate the physical movements you need to get them. And we can really see how critical dopamine is when we look at what happens when that delicate balance gets thrown off.
And I mean, this balance is unbelievably delicate. Have too little dopamine in a key part of the brain that controls movement, and that's a defining feature of Parkinson's disease. On the flip side, have way too much dopamine activity, and that's linked to the symptoms of schizophrenia. It's a chemical that lives on a razor's edge.
Okay, so we've talked about the brakes, the gas, and the fine-tuners. We've got our key players. So now, let's apply all that knowledge to one of the most incredible feats of modern medicine, cracking the code of consciousness by figuring out how to safely and intentionally turn it off.
This, of course, is the world of general anesthetics. We're talking about drugs that have this absolutely remarkable ability to produce a temporary, completely reversible loss of all feeling and, this is the big one,
consciousness itself. So how in the world do they do it? It's not magic. They actually hijack the exact same system we've just been talking about. They basically come in and slam their foot down on the GABA brake pedal, making it way more powerful. At the very same time, they cut the fuel line to the glutamate gas pedal. The result? The whole system just quiets down.
But putting someone under isn't like flipping a switch. It's a very carefully controlled journey through 4 distinct stages. It starts with just losing the sensation of pain. Then it moves through a brief, tricky stage of delirium before it finally lands in the target zone, surgical anesthesia, where the body is totally unresponsive. But there's a 4th stage, a dangerous overdose, which is exactly why this whole process is monitored so carefully.
And to manage that journey, anesthesiologists have an entire toolkit of different drugs. Some you inhale, like gases or liquids that turn into vapor. Others are given through an IV. And they'll use different drugs depending on whether they need to put someone under really fast or keep them in that state for a longer, more sustained period. And this brings us to the final and maybe the most mind-bending idea of all. The fact that we as humans can reliably and safely turn consciousness, the thing that makes you, off and on again, just by tweaking the balance of a few simple chemicals. That's absolutely staggering. It really forces you to ask a pretty profound question. If our consciousness can be controlled so precisely by our chemistry, what does that tell us about what consciousness really is? Something to think about.